Recently, we've been talking a lot about regression and conditional probability estimation. And the way we've been approaching these problems is to phrase the learning task as an optimization problem, defining a suitable loss function, and then looking at ways to minimize it. What we're going to do now is to circle back around to classification, bringing with us this new optimization-centric mindset. So we'll talk about binary classification and how it might be solved using a linear separator. We'll define a suitable loss function for classification, and then look at a stochastic gradient descent procedure for it, and this will yield the perceptron algorithm. Okay, so here is a linear boundary in R2. What is the equation of this line? Okay, so let's go ahead and figure this out. So we have, let's call this feature x1 and this feature x2. The equation of this line is something of the form x2 equals the slope times x1 plus the intercept. Okay, so what is the slope over here? It's minus 4th hertz. So minus 4th hertz x1 plus the intercept on the y-axis, which is 4. That's the equation of the line. Okay. Now we'll be writing it in a slightly different way. So let's multiply through by 3, and then this becomes 4x1 plus 3x2 minus 12 equals 0. And we'll always be writing linear decision boundaries in this way, in the form w dot x plus b equals 0. Okay, the form w dot x plus b equals 0. So that's the equation of this line, and that's going to be a decision boundary. Points on this side, we'll say are plus. Points on this side, we'll say are minus. Now, how do we make a prediction on a new point? So let's say we get a new point x, maybe this point over here, 3, 3. How do we predict the label at that point? Well, we plug it into our linear function. So we have this linear function over here. We plug in 3, 3. What do we get? We get 4 times 3, 12, plus 9 minus 12. That's 9. That's greater than 0. So we classify it as positive. Okay. Let's take another point, maybe 1, 1 over here. Let's plug it into our linear function, 4x1 plus 3x2 minus 12. What do we get? We get 4 plus 3 minus 12. What is that? That is negative 5, and that's less than 0. So we classify that point as negative. So the classification rule is very simple. When we get a new point, we simply compute our linear function, which is 4x1 plus 3x2 minus 12. And then we look at the sign of that. So we take this and we look at its sign. If it's a positive number, we say the class is plus 1. If it's a negative number, we say the class is minus 1. Okay, so in a little bit more generality, if we have data now in d-dimensional space, so points x in Rd, and two possible labels, plus 1 and minus 1, this is a general setting for binary classification. Okay? And we're going to be looking at situations where we have a linear classifier. So there's a decision boundary, which is linear. It's of this form, w dot x plus b equals 0. And here, w and b are parameters. They're the parameters of the linear function that we have to figure out, typically from training data. Okay, so these are our parameters over here. And when we get a new point x, and we have to predict its label, plus 1 or minus 1, the way we do it is we compute this linear function, and then we just return its sign. We just see whether it's positive or negative, and that's the answer. Okay, so when are we correct? Okay, so let's say we get a new point xy. When are we correct on that point? So we're correct if the label of y plus 1 or minus 1 has the same sign as w dot x plus b. So y has the same sign as w dot x plus b. Okay, and to spell it out even more, what that means is that either y is plus 1 and w dot x plus b is greater than 0. Let's say greater than 0. Or y is minus 1 and w dot x plus b is less than 0. If that happens, then we're correct. And now we have two conditions over there. We can combine them into a single, more concise condition like this. We can just say that y times w dot x plus b is greater than 0. Either they're both greater than 0 or they're both less than 0. Okay, so this is a nice, concise way of writing the condition that we're correct on point xy. And we'll be using this formulation quite a bit more. Okay, so now let's come up with a loss function for classification. So we have some linear classifier given by WB. And we want to know what is the loss incurred by this classifier on a point xy. How should we define this loss? Should we use squared loss or logistic loss? What's a suitable loss function? Okay, and there are actually many ways to do this. There are many different loss functions for classification that all have their strengths and weaknesses, and we'll just look at one particular plausible loss function right now. Okay, so we have a point xy. Let's say we are correct on that point. So y times w dot x plus b is greater than 0. If we're correct, we'll just say no loss. We're correct. Nothing to worry about. Okay. On the other hand, if we are wrong, if y times w dot x plus b is less than 0, if y and w dot x plus b have different signs, then we're wrong. How much penalty should we incur? Well, one thing we can do is to say that our penalty is the amount by which we are wrong. Okay, so what does that mean? So let's say that the correct label is plus 1. And when we compute w dot x plus b, it turns out to be negative 0.1. So we're wrong, okay, because we predict minus. But we're only wrong by a little bit, only by 0.1. So we shouldn't feel too bad about it. Okay, so in that case, we'll think of our loss as being just 0.1. On the other hand, if y equals plus 1 and w dot x plus b equals minus 6, then we're pretty far wrong. Okay, we also predict minus, but this time we're really far from that boundary. Okay, we're at minus 6, and so in this situation, we'll say our loss is 6. So here's sort of a picture of the loss function. Okay, so over here, I'll draw the possible values of y times w dot x plus b. And we want this to be positive. Okay, so we'd like this to be on this side of 0. And now let's look at the loss. I'll draw that on the y-axis. So if we classify the point correctly, then our loss is 0. Okay, then we lie along this line. No loss at all, we're correct. If we are wrong, then our loss looks like this. Okay. Now, one notable feature of this loss function is that it's convex. Okay, why is that? Because if you look at any 2 points on the curve and you connect them, the graph, the curve, lies below that line. Okay, so this is a convex loss function. Okay, that's something that should, in general, make us feel good. But now let's go about trying to find a linear classifier that is minimizing this loss. Okay, and we could do that by gradient descent if we wanted to. But to keep things really simple, let's just use stochastic gradient descent. Okay, so the way this is going to work, this is a local search method. So we start by setting w and b to any old values. Let's say we start them at 0. And then we keep updating them. So we update w and b a little bit, and then we update it some more, and we keep going in this way. And in stochastic gradient descent, each update is just based on a single data point. So we first update on the first data point, then we update on the second data point, and we keep going through the data set. And when we reach the bottom, we cycle back around to the top and then update on the first point, second point, and so on. And what are these updates? The update is to take W and B and then move in the negative direction of the derivative. Okay, so let's work that out. So we have our current guesses, W and B. Okay. A new data point arrives, the next on the list. That's some point X and Y. What's our update going to be? Well, let's say we actually get X and Y correct. Okay, so let's say Y times W dot X plus B is greater than 0. In that case, the loss is 0, okay, and the derivative is 0, so there's no update. Okay, that's easy. What if we get it wrong? What if W times X plus B has a different sign from Y? Okay. In that case, the loss that we formulated is minus Y times W dot X plus B. And what is the derivative of this thing? Okay, so let's see. What is the derivative of this with respect to W? Well, it's just minus YX. And what's the derivative of this with respect to B? It is just minus Y. And so the stochastic gradient update in this case would be to take W and move in the negative direction of the derivative. So we take W and we go plus YX, and we also have a step size eta. And we take B and we also move in the negative direction. So step size times Y. That's the stochastic gradient update. Very simple. Well, there's the matter of the step size. We have to decide what to set eta to. And let's just keep things extra simple. Let's just make it equal to 1 so we can get rid of this. So that's going to be our update. And when we do things in this way, we get the perceptron algorithm. So here it is. Very simple algorithm. We start W and B at 0, and then we just keep cycling through the data. Okay? And if we're correct on the next data point, there's nothing to do. If we are wrong on the data point, then we simply take W and add YX to it, and we take B and add Y to it. That's it. This is literally 4 lines of code. Okay? Let's see it at work. So here are 85 data points, and they're linearly separable. So there really is a line that separates the pluses from the minuses, or in this case, the red circles from the black triangles. Let's run the perceptron algorithm on this data set and see what linear separator it finds. Okay? Now, usually when you run perceptron or a stochastic gradient descent algorithm of some kind, one thing that is often done is to begin by randomly permuting the data, okay, in case they're in some sort of weird order. Okay. Now, in the case of perceptron, different random permutations can lead to different outcomes. So let's just look at several runs. Okay. So this is the first run. It found a linear separator that perfectly classifies the data. Okay. And it made 9 updates. So what I mean by that is that if we go back to the algorithm over here, this is what I'm calling an update. When it gets to a point on which it's wrong, it updates the parameters. Okay. So in this case, it only did 9 updates. And once it did those 9 updates, it cycled through the data set and it was correct on everything it saw. Okay, so it stopped at that point. Here's another iteration. This time it made 15 updates. Another one, this one did 8 updates. Another one, 14 updates. Another one, this one was 8 updates. Okay, so here's one question. Okay, so in this case it did 8 updates. What do you think the final value of B was in this case? Well, let's go back to the algorithm. So B starts out at 0, and each time you make a mistake, you change B by adding Y to it. Now Y is either plus 1 or minus 1. So each time you do an update, B either goes up by 1 or goes down by 1. That means that if you make 8 updates total, the final value of b is an integer, which is somewhere between -8 and +8. Okay? So that's something we can infer just from the fact that there were 8 updates. Okay, so we had these multiple different runs, and every single time it found a perfect classifier. And in fact, this wasn't just a lucky data set. The perceptron algorithm is guaranteed to do this. Okay, so there's a mathematical theorem that says that if the data is linearly separable, in other words, if there is some linear boundary that separates the pluses from the minuses, then the perceptron algorithm will find such a boundary. It's guaranteed to, and it'll converge within a finite number of steps. Not bad. A 4-line algorithm that is guaranteed to always return the correct answer. Now, if we have a data set like this, for instance, so here we have 8 points, what this theorem is telling us is that the final answer is going to be some separator like the ones shown. Okay, something that separates, something that really does separate the reds from the blues. Now, one thing one might think at this point, now that we have this under control, maybe we can get a little bit greedy and say, well, maybe these are not all equally good. Can we get something that's more central, maybe something that's right in the middle? And that's exactly the question that we'll tackle next time. Okay, so for now, that's it. We have seen the perceptron algorithm, and we derived it by formulating a loss function and looking at the stochastic gradient descent algorithm for that loss function. And the result is a 4-line algorithm that any of us could code up in 5 or 10 minutes. It's one of the real gems of machine learning. See you next time.